Here we are once again. It's the physics video lecture. psci 168, video lecture 11. So I have some stuff out here this morning, and we have to do some review, but let's get the topic up here. We're going to review free fall, and we're going to take the subject all the way to orbiting satellites that orbit our Earth. So free fall to satellite orbits. So we needed the study of motion. We had, of course, we're trying to understand energy, and we got pretty far actually: force, work, potential energy, power. But we had to take a serious detour into the science of motion, which is what we've been doing for a couple lectures, and we're going to continue with that. So we had the science of free fall. And when I'm talking about free fall, I'm just talking about dropping something and catching it, or launching it and catching it. And what makes it free fall is that there's no friction. We were trying to find the law of free fall. And so let me go ahead and list a couple of things. So first of all, motion. We had some kinematic concepts. We had position, displacement, velocity. This one I'm going to remind us of. V equals displacement over time. And I can call this delta t or t, it means the same thing. If I put a line up here, I'm talking about average velocity. Average velocity. We can use these interchangeably, it all depends, okay. Meters per second. Then we had acceleration. And that was just building the concept the same way we did this one, was the change of velocity over the change of time. And the units of acceleration were meters per second squared. So review this. Then we had free fall is motion. Here, I'll start that up here. Free fall is motion with constant acceleration. Lack of friction, hammer, feather, remember the feather, all of that. But once we get to the essence of it, is motion with constant acceleration. And we ended with the formula for free fall. And there is a systematic derivation of this, but once we had the constant acceleration, we knew that the distance fallen was going to be proportional to the time squared. The proportionality constant is 1/2 g, and that g is 9.8 meters per second squared. It's called the gravitational acceleration, or the acceleration due to gravity. Here, I'll write that down here. Acceleration due to gravity. Okay. So there's our formula, and we even plugged in a couple of numbers to see what it means. But the distance grows very rapidly as time increases until friction takes over. But if you drop a brick, say, from a tall building, it's going to accelerate for quite a while and obey this law. It's the distance times squared law. Yeah, so that's free fall. Now, I'm going to spend a little more time on the free fall kinematic equations before I demonstrate some stuff here. see, I'll have to erase this board. Yeah, I'm gonna erase this board. We're gonna get a couple more formulas going here. And then I'll demonstrate a couple of things. So what I'm going to do here is write, without deriving them, the kinematic equations This is free fall when we release something from rest. I should state it works just as well when you throw something in the air and then it stops and comes back down. So the kinematic equations for free fall, we have, and free fall from rest, yeah, let's just keep them really basic. We have h is equal to 1/2 gt squared, so that's the distance fallen when I drop something. And when I drop it, it means I released it from rest. Here it is at time equals 0, and then it falls. Okay. So make a point of that in your notes. And then the speed that it has achieved grows linearly in time. Okay. So for example, speed. So for example, after 1 second, you would have 9.8 meters per second times 1 second. Okay. So let's go ahead and do that as an example. V equals 9.8 meters per second squared times 1 second, and one of these seconds is going to cancel seconds, and so we'll end up with meters per second. 9.8 meters per second. Notice this 9.8 is not the same thing as this one here. This is an acceleration, this is a speed, but it's a good point to make because after 1 second of free fall, the object is moving at about roughly 10 meters per second, which is as fast as a man can run, right? So that gives you an idea of that. Now what we can do is plug one of these into the other. So if we solve for t and plug in up here, we have h equals g over 2, and then we're going to solve for t. T is v over g. V divided by g, and we're going to square it, and that gives us v squared divided by 2g. This third formula here, I'll put a star there, and in fact I'll go ahead and put a h equals v squared divided by 2g. This tells us how fast something is going in terms of how high it, the distance it fell through. So there's no time in this expression. But yeah, these are the 3 kinematic equations that we're concerned with in this class. Okay, so the law of free fall, the speed, and then the combination of those two, which gives us the distance fallen, expressed in terms of the velocity squared here. I'm going to do one more example. So let's just go ahead and call this example for free fall, because you want to be able to practice these things a bit. I wouldn't mind if you guys made up a half a dozen examples and just tried them out. So how far does an object fall in 3 seconds? Okay, how far does it fall in 3 seconds? So h is going to be 1/2 9.8 meters per second squared times 3 seconds the quantity squared. This is how we always evaluate these. We know 9.8 over 2 is going to be 4.9. Okay. Now, in terms of the units, we have meters per second squared, and here in the numerator we have seconds squared if we multiply that out. So I'm actually going to write this meters per second squared times 9 seconds squared. So if you do that, then these cancel and you're left with meters, and the answer is 4.9 times 9. So 5 times 9 is 45, so that's just under 45. Okay. So I'm just going to leave it out as 4.9 times 9 meters. Approximately 45 meters. And that would be approximately 140 feet or so. But yeah, we want to learn to just think in terms of meters, and it's not that difficult to do. There's the meter right there. So approximately 45 of those in 3 seconds. So this is an example of how to evaluate these formulas. All of these quantities have units, and they're always in terms of meters and seconds, and you just go at it like I just showed you. Okay, so what's next? Now that we have some practice with the free fall, and you definitely want to make sure these things are listed carefully in your notes, these 3 formulas here. I want to do some demonstrations. I'm saying that we're going from free fall to satellite orbits. How's that going to work? So what do I have here to demonstrate? I have a cart that rolls very smoothly. Wish me luck on this, by the way. And it has a little built-in device. So I put a ball in there, and it's going to trigger right here, and it just shoots it up in the air, and that's free fall. Okay, this thing was launched vertically, it was free falling, came back down. Okay, so on the way up, it was just the reverse of this law. Still the time dependent, so it took 2 times, time up, time back down. Let's try this again. The more I try it, the less likely it is to work every time, right? Okay. So that is free fall. And you'll notice straight up and straight down. Now what if I combine the 2 motions? So what I'm going to do is set this up and launch this to the right. See what the camera captures, by the way. I'm counting that as a success, but let's try it again. As long as it lands in the basket, that was a success. But with any luck, I can also keep it from bouncing out. So once more. That was good, okay? So how is it possible for this ball to be caught down there? It really doesn't matter how fast I launch it. If I do a really slow one, it'll catch it. And if I do a much more rapid one, it'll also catch it. There we go. Okay, I better declare victory, right? That worked several times in a row. Yeah, the question is, how does that work? There's no skill involved on my part. What's happening is the following. The law of free fall is still in play, and the forward motion is completely independent of the vertical motion. So that's the point we're going to make now. The forward motion, the horizontal motion, is independent of the vertical motion. Horizontal is constant velocity, vertical is free fall. Here's another way to look at it. If you were sitting in this cart, okay, if you were sitting in here, and the can and the ball were launched just beside you, you would see it just coming up and back down right next to you. Okay. You can do this in an automobile. In an automobile, you could be in the passenger seat and throw something like that as well. So this independence is the key. Another interesting aspect of this demonstration is that I can compare it to a little projectile cannon that I have here, and I'll do that as well. So let me put a couple of these ideas on board, and then we'll continue on. By the way, one thing you might do is if you get a good screenshot, print out a screenshot and put it in your handwritten notes and show me that you have that. So the name of this demonstration is called the projectile cart. So demo projectile cart, and apparently here we are on a horizontal track. We have this cart here, and it's capable of throwing a ball straight up in the air. That's all this cart could do, throw the ball straight up in the air. If the cart is moving, then this straight up in the air here, I'll indicate motion, the straight up in the air motion is combined with a horizontal motion. And since we've studied vectors, we see what's happening here. We're getting a velocity at an angle, and that velocity at an angle allows the cart to catch the ball over here. Here's point 1, here's point 2, there's the trajectory, it catches the ball. The only way that can work is if the vertical and the horizontal motions are independent. So that's what I'm going to put down here. Projectile cart, you guys right, catches the ball. Vertical motion. And what was the vertical motion? Free fall, accelerated motion. Is independent of the horizontal motion and what was the horizontal motion? Simply constant velocity. And constant velocity motion is also called uniform motion. So I'll just put that there as well. Uniform motion. So it's this independence that makes all the difference, or that makes this possible. So the two motions are independent. Again, the little cannon just spits the ball straight up and down. It's combined with the forward motion, and what you get is this arc. And because they're independent, it's the same as if you sat in the car and threw the ball straight up and down and just moved along with it. So let me demonstrate something else that's just related. And like I said, that's this little cannon here. So we'll call the cannon the projectile launcher. And you guys draw a picture of it. Put the target right here. And you'll notice with this cannon, it's at about a 45-degree angle. Okay. So the launch angle is along my ruler here. That means, since we know about vectors, it has an up component and a horizontal component, just like the projectile cart did. Consequently, if I aim this thing right, it should make it in there. Okay. That's the same parabolic arc that we had with the projectile cart we have here with this cannon, projectile launcher. It's interesting to see how this shows up on our video. Okay. And there's if you study physics, you learn about the science of the angle and the speed and the distance, and all those things can be done with great accuracy. But for our purposes, we just need this independence of those two motions. Okay, so I'll draw a little picture of what we had here as well. Okay, so for our projectile launcher, we have X and Y if you want. We have an initial angle, theta. We have an initial speed, but of course there is this vector here, this initial velocity vector, has a forward and a vertical component. We've just seen that, and the upshot is that we get this parabolic trajectory. Okay, now here comes an interesting point. Suppose you start at the top. You notice this thing's rising and then it's falling. Is this a big enough picture? Yeah, we'll work with this picture. We're gonna have another one in a moment. So rising and falling. There's the trajectory, and if you go to the very top of it, at one instant it's neither rising nor falling, it's horizontal. Okay, so I'll put a horizontal blue arrow there. That's the velocity at the top of the trajectory. It's a horizontal trajectory. So if you were to start right here, you could say I'll be up on this hill here and I'll do a horizontal throw, and then I'll get the second half of this trajectory. And let me consult the clock here. Good. Perfect. So let's put this as a note. At the maximum point of our trajectory, maximum point, we have, for that moment, horizontal motion. Horizontal motion. Put an exclamation point there. That's what I'm going to use now to continue on. Good. So this, by the way, this motion here with the cart, this motion with the cannon, they also are free fall. Okay, they're just free fall with an added horizontal component, but the vertical motion is completely just free fall. If you start from the top of the trajectory here or up here, doesn't matter. Start from the top of the trajectory here, you're moving horizontally, and then you arc down in a parabola. Okay, and this height h here, let's even label this height h is the same formula in our it's the same h in our h1/2 gt squared. So that means this horizontal throw here is going to take just as long as it would to drop it straight down. Okay, that's why I have to show this demo and really explain it. So I can throw this thing horizontally, but it's really just falling straight down at the same time, and that's how fast, that's how long it's taking. That's the formula for it. So having said that, let's talk about the horizontal throw specifically. Good, so I'm going to erase this. We've seen these two demonstrations. So this time we're drawing a much larger graph. This one should fill the entire width of your page. Okay. So we will have two axes, make a pretty wide one here, but I still need room to write some words. Here's our x-axis. Here's our y-axis. We're going to start here from height h. In fact, I'll make that h a little more generous. Let's go up here. H, okay. We're going to do the horizontal throw. Imagine pitching a baseball, okay, horizontally, perfect horizontal release, or maybe a tennis ball is hit from the racket and it's, the minute it's released, right, it's moving completely level at that instant. That's the horizontal throw. So I'll put a little arrow here for that. Yeah, okay, this arrow represents V0, that's the speed that we throw it with. 5 meters per second, 10 meters per second, take your pick. Point is, the trajectory is this part of the parabola, and the ball lands there, okay? Now the question is, so this is distance 1. The question is, how far does it go if I throw it with twice the initial speed? So D1 or here, D0 for V0. That's the distance for the initial speed. Now suppose I throw it with twice the speed. Twice the speed means it's going to go twice the distance in the same time. But the time it falls is always the same time. So if I do twice the speed, I'm going to go exactly twice the distance, okay? 2d0 for 2v0, and I'll draw this arc. Your arc may be better than mine, but it's an example. And you can see where I'm headed with this now. What about 3 times the initial speed? Yes, 3d0 for 3v0, because the time is always the same, however far long it takes to fall down. How far is that, by the way? So if we have h is equal to 1/2 gt squared, t is equal to 2h over g square root. Okay. See if you can do this, by the way. Leave some space in your notes and see if you can go from this equation to this one. So yeah, that time is always the same. And I'll draw my last 3v0 here, and I'm going to make my point. As long as there's no friction, I could throw it 10 times as fast and it would go 10 times as far. So make a good note of this. Next. Can I keep doing this? Okay. This is all horizontal throw, no friction. Friction would ruin this, okay? No friction, so maybe there's no atmosphere when we're doing this. So next is, what if I do this with 10 times, 100 times the initial speed? Yes, 10 times, 100 times that initial distance. Now there's a special speed in which the curvature of our arc here matches the curvature of Earth. I think I'll do this in black. Text, the speed v0 at which the parabolic arc matches the curvature of Earth. Because if the parabolic arc matches the curvature of Earth and there's no friction, then you've just launched a satellite into orbit. Okay? Then you'll turn this thing, instead of the ground being level here, it's really a spherical Earth. and it's a circular path. Okay, so that's what I'm going to do next. I have to erase these things. Let me consult the clock again. I think we got this in the allotted time. Yes, we do. So we're going from a horizontal throw to a satellite orbit. Okay, so let's write this down. From horizontal throw to satellite orbit. So let's see, we're going to draw a sphere this time, or a circle. By the way, here again, we need a nice sized circle in our notes. The idea is, in fact, we're going to do two circles. So first of all, the idea, and there's some nice pictures online. See if you can find this. It's actually from Isaac Newton's book. Imagine if you shoot a cannon with a certain speed, you double the speed, you keep increasing the speed until what happens? Until you match the curvature. Then, this last speed, since there's no friction, you're just tracking all the way around the Earth, and in fact, you come back to where you started. Okay. So there's a particular exact speed with which we can do that. Let's go ahead and just say we have a radius of Earth here. Radius. Now for my second picture, I'm going to do the calculation. So now it's going to be a construction. And we have a radius, we have a distance forward, which we're going to call L, and we have a hypotenuse. Notice the horizontal throw gives us a right angle right there. So this is also R, but that little bit is H, and H is equal to the distance fallen in 1 second fallen in t equals 1 second. And what about L? L is the distance forward in t equals 1 second. L equals forward motion, forward distance in t equals 1 second, right? It's the same 1 second, just what we were talking about before with the horizontal throw. Well, what you'll see here is that we have a nice geometrical construction. Since L is the motion forward in 1 second, we have V, so orbit is going to be equal to distance over time, right? Speed, distance over time, that's going to be our orbital speed. So it really looks like we've got a construction here. It's going to lead to success. So I'll use the left side of the board here, and I'll show you guys this calculation. We're going to use the Pythagorean theorem, so I'll just number my steps. 1, Pythagoras, and we're going to say R squared plus L squared equals R plus H, the quantity squared. Then we expand this out, so we've got R squared plus L squared equals R squared plus 2RH plus H squared. Again, there's a step that you may want to remind yourselves of, but it's not hard. So I've expanded that out. These guys go away, and now I'm going to solve for L. L is equal to just the square root of the right side, okay? So L squared is equal to what's left. Take the square root of both sides, RH plus h squared. Now here's a step that we have to realize that h is on the order of 5 meters and capital R is on the order of 6 million meters, so that h is so much smaller than r that we can neglect the h squared. So I'm going to write L equals root 2RH plus something small. Now, I could put a little squiggly line here for approximate, and then I'll write because h is much less than r. So the error that's made in this calculation is, a fraction of a percent. It's very small. Okay. Because 5 divided by, roughly 5 divided by 5 million. Okay. So it's 1 millionth. Okay. So it's a very, very small error. So this is the expression we're going to evaluate. Now, what do we have? R for the Earth is equal to 6.37 times 10 to the 6 meters, and h for 1 second is equal to 4.9 meters. So what you're going to do, I'm going to do, but you guys plug it in with your calculator. We're going to get L equal to 2 times 4.9. Well, let me do the other order. 2 times 6.37 times 10 to the 6 meters, and then I've got 4.9 meters. You guys should do this with your calculators. You're going to get approximately 7,900 meters. So now we have found the orbital speed. The orbital speed is going to be 7,900 meters per second for a near-Earth orbiting satellite. I'll put that right down here. For near-Earth circular orbit, that's orbit, the orbit, I'm just going to write the equal, 7,900 meters per second. Okay. Once more, I'll consult the clock. Okay, perfect. So this is our grand result. We've taken it, by the way, we discussed the shape and size of Earth, so we know how this number was obtained. If you know this, right, the meter. So we've done this, we've studied free fall, right? This here, remember this came out of h equals 1/2 gt squared. So this is a result we've gotten fair and square all the way from the beginning, and now we know the speed of an orbiting satellite around the Earth. And notice, that's pretty fast. 7,900 meters per second is pretty fast. We'll start with this next time. This is a good point to stop. You guys should practice this calculation, okay? In in-class exams, I always include one like this. For you guys, I'm going to do something similar. I could easily do something like this where instead of we use Earth, we use the Moon or Mars or something, and the numbers would come out different, but the process would be exactly the same. So I'll leave you with that. See if you can find some images to print out for these things. See if you can find some images that that example with the little mountain and the cannon shots, that was from Isaac Newton. So maybe if you look up Isaac Newton orbits you'll even find that picture. So see if you can find some nice pictures to print out. Good. So until next time, enjoy.